Alright, Chapter 7, Engineering, Mechanics, Statistics, Masad Ali, PhD, Professional Engineering Introduction. Statistics study the body with the rest of the body with the rest of the force acting with the body with the balance. Each of the chapter presentation with the concept of the state with the static equivalent particle with a rigid body with the followed by the discussion determination external and internal forces of the structures such as trusses and frames, moments with the centroids with the plane areas and basic concept of the friction. Also the discussed following is a complete list of the chapter contents. Forces, momentum, and equivalent particle with equivalent rigid body of the trusses and frames, friction, center gravity, moments of an area, and summary. 7.1 Forces, except the push or pull exerted one body with another force, a vector of the quantity which have the magnitude of the direction. Forces are classified external, internal, and concentrated, distributed, shown figure 7.1. Shows concentrated, distributed in internal forces, concurrent forces, non-concurrent forces, partial parallel forces in figure 7.2. A force system is classified by the concurrent and the non-concurrent. All forces acting on the body pass through the same point, but the force system is called the concurrent. All forces acting on a body that do not pass through the common point with the force system is non-concurrent. The resolution of force is resolved along with the two arbitrary axes, the more convenient, the efficient. However, the result of the forcing along with the y and axis is the Cartesian rectangular coordinate system. The appropriate equations as follows. Force x is equal to force cosine 0, force y is equal to force sin 0, and it shows the figure 7.3 sample and solution figures. Resultant concurrent forces system 2D the resultant may be the result of the two rectangular resultant x and resultant y. Resultant is equal to f1 plus f2 plus f3 to the equal to the logarithm of f. Example, find the resultant forces, solution. Resultant force of 3D, the result force in components with the x, y, and z. The two methods available. If the angles between the force x over the axis x, y, and z are known, show them see figure 7.7, and then force x equal to force cosine, force y is equal to f cosine y, and force z is equal to cosine z. Also, the relation between the angles such as the cosine 2, cosine x, y, and 2 z are equal to 1. Method 2, in coordinating with the 2 points of the long line of action, force again is given in figure 7.9. Unit vectors, unit vector AB, the express result of the force and the coequivalence force. Combinate unit equals unit vector AB. Unit vector AB equals dxi, dij, dxi, and z over d, or d is equal to the square root of d squared, d2 x squared, d2 y squared, d2 z squared, where I, j, and k are unit vectors x, y, or z axis respectively. D is the distance between 2 points, A and B along the line of action of the force. For resultant and concurrent forces of the system 3D, similar to the two-dimensional case exempts, their third component RZ. The equations are as follows: Rx is equal to the logarithm of fx, or y is equal to the logarithm of fy, and Rz is equal to the logarithm of fz. R is equal to the square root of R's x squared, or y squared, or z squared. OX is equal to cosine -1 to the RX over R. The angle of Y is equal to cosine -1 over the RY over R. OC is equal to cosine -1 RZ over R. Alright, so we have solutions. 7.2. Momentum is the force of the pressure tends to be the rigid body with the rotation of the axis. Moment is divided into 2 parts. Moment is single force and moment of couple. Moments of single force and moments of a single force can be at one or at a point, or 2 at an axis. Moment of the force about a point is the product of force with the perpendicular distance for the point of the line of action. Force, therefore, magnitude of the moment about point A expressed by the equation MA equals force times distance. Distance is perpendicular distance from point A. The line of the action is force F. Line of action of force F and distance A. Figure 7.12. The direction of the momentum clockwise rotation force F at about point A. The moment of the determined vectorially is given in an equation. Moment of Moment of force A is equal to the position of the vector times the force, where R is the position of vector point A is anywhere along the line of action of force. Or to be efficient, you should moment of couple with two equal parallel forces with a non-collinear linear line action with the opposite of the sign for the couple with the figure 7-16 with the moment of the couple is product of the force shortest distance between the two forces. Note the equation below. The moment of couple is the same with respect to any of the point in space. Shows moment of couple equals force times distance. And it shows parallel perpendicular lines and rotary forces. 7.3 equilibrium particles. Two-dimensional case of the four-particle equilibrium at rest result when the force acting on the particle must be equal to 0. There is no translation. Rx is equal to the logarithm fx equal to 0. Ry is equal to the logarithm f force y equal to 0. Three-dimensional case in the same case for the two-dimensional case, except that there is a component in the z direction. The resonant moment is equal to the logarithm fx 0. Resonant y movement is equal to the logarithm of force of y. Resonant z movement is equal to the logarithm of the force of z equal to 0. 7.4 equilibrium rigid bodies. Two force members. A member under the action of two forces over the different points of the body, but the member is called the two force member. The trade with the two force member, the force acting along the axis member tension and compression. The force member is not straight, but the force must be acting along the diagonal line connecting 2 points where the two force acting in figure 720. Connecting supports and reactions. Rigid bodies that either connected to each other result on the surface of the most cases necessary to determine the resulting reactions. Different supports defined by the number, the type of the reaction given the support will determine whether the point of contact with the translate with the rotate with the point cannot translate a force reaction along the line of the translation x, y, and z is required with the point can rotate moment of reaction about with the x. This is required in Table 7. Equilibrium equation 2D for the rigid equilibrium found, the equation must be specified. Resultant motion is equal to logarithm of x equal to 0. Resultant motion in y is the logarithm of force on y equal to 0. And logarithm of motion is equal to 0. Figure 720 shows a straight force, two members. Straight, non-straight, two force members. This means that the body will neither translate nor rotate. Equation 712 of the momentum can take any of the point of the body. Note that the two-dimensional case of the three equivalent equations, so that there cannot be more than three unknowns if given in the free body diagram (FBD). And it's got its examples and equation, table support, rigid bands, connection support, hinge pin reactions, numbers unknowns. Rough surfaces, reactions 2, roller, rocker, smooth, reaction perpendicular 1, fixed 3, ball and socket, RX, RZ, RY, RZ, or Y, fixed RZ, momentum 1, or Y, MY, X, MY, X, 6. Figure 723 equilibrium equations. If in this case there are 6 equilibrium equations, 3 force equations, 3 moment equations. Resultant equation, resonant reaction over the logarithm of force x is equal to 0. Resonant of y is equal to 4, and logarithm of force y equals 0. Resonant z is equal to logarithm of force z equals 0. Logarithm of momentum of the x is equal to 0, logarithm of momentum y is equal to 0, logarithm of mz is equal to 0. Note these are three-dimensional problems. We cannot have more than 6 unknowns. First parentheses represent the logarithm my, and the second mz. Set each trusses in frame 7 and 5. Truss is a collection of rigid body with a pin connected with each of their end of the form of the new rigid body known as a truss. Each member of the truss is a straight two-force body with the main objective is to determine an internal force sum of all the members of the truss. Each member can be in tension or compression depending on the loading and configuration of the truss. Generally, two methods are available to determine the internal force given the truss: method of joints and method of sections. Method of joints. Use the method of the FBD of the joint applying with the two-dimensional equilibrium equation to each action. The resultant Rx is equal to logarithm of Fx equal to 0. Resultant y is equal to logarithm of force on y equal to y. Note that they are given in joint, but there cannot be, and there are more than two unknowns. Alright, then it gives an example. Method of sections. This method, U of the force for the few of the member of the large truss to determine the cut with the truss section of the force be determined, shown in figure 728, with the conservative section on the left, right, up, down. In other cases, draw with the FBD with applied with the two-dimensional equilibrium equation with the rigid bodies. Generally, with the section considered shall not pass or cut more than three members at a time, since the only three equilibrium equations are available. Rx equal to logarithm of Fx equal to 0, Ry is equal to logarithm of Fy equal to 0, and momentum M is equal to 0. Note that there are some trusses necessary to determine external force reactions, but solving the internal forces. Alright, frames. Frames are structures containing multi-force members designed to support applied loads. Frames are usually stationary. Everything analyzed done with a disassembling of frames, shown in figure 730, drawing the FBD with each member applying with equilibrium equation. Note that some of the members of the frame are going to be two-force members. Resultant x is equal to logarithm of force x is equal to 0. Resultant y is equal to logarithm force y equals 0. The logarithm momentum is equal to 0. Alright, 7.6 friction. Two surfaces of the contact of force tangent of the surface that oppose the direction into the motion is called friction. There are two types of friction: dry friction, fluid friction. To understand the dry friction, consider the figure shown below with the maximum value of friction force. Friction max is related to normal friction force and coefficient with the static friction US. Force max is equal to the coefficient status friction times normal force. Two types of friction problems. There are two distinct types of friction problems. One, impeding motion exists for the object with the bow to move. In the case of friction reacts for the reach for the maximum value of the force equal to the force max over the static coefficient static max for the number of normal force. Applied with the equilibrium equation particle with the rigid body, solve the unknowns. Impeding motion if it's not known, you don't know whether or not the object is moving. They can assume that the system's equilibrium applied with the appropriate equilibrium equation particle rigid body, solve the friction normal forces. For two outcomes are possible. Force is greater than static coefficient times the normal force. The system is equilibrium friction force calculated is correct. Force is greater than static and coefficient normal force. The system motion of the particle problems only correct the value of the friction force. Force is equal to the coefficients of the friction over the nominal force. The nominal force is called the coefficient kinetic energy, and the general kinetic energy is about 25% smaller than the coefficient of static friction. For rigid body problem of dynamic analysis, you have to determine the magnitude of friction force. Alright, belt friction. Consider belt pressed against a rough and curved surface and pulled on both ends. Friction with conservative tension on both ends with a note the same, and it can be shown with the tension 2 and equals tension 1 over the energy of the static coefficient, with a 0 is the angle of the current contact between the belt and the drum. Then it goes an example solution. Screw friction. Screw friction is the subject of the axial load friction force developed to determine the momentum needed to determine the screw. Following equations can be used, where M is external moment, P for the axial load, R is the radius for the thread, A is the leading angle equal to the A of the tangent, and the negative 1 over 2 pi R radius. I think that's, and tangent 1 and plus is equal screw tightening, negative screw loosening. Shows example. 7.7, the center of gravity is defined with a point of body where the weight of the body passes through for the homogeneous body with the center of the gravity similar to known as the centroid. General determine the location of the centroid plane area of the following is the XC is equal to X of the derivative of x dA over a yc is equal to the derivative of yc dA over a, where the derivative of xc and dA and the derivative of yc dA is called the first moment of the area with respect to the y-axis and the x-axis respectively. If the plane area divided by the common shape shown in figure 740 of the rectangular semicircle, the triangle over the distance discrete with the form of the equations of the follows as xc is equal to the logarithm of xi ai over I. Yc is equal to logarithm yi times ai over a, where x and y are coordinates for the centroid common shape relative to the reference. Selected reference, refer to table 72 areas of the centroid over the common shape. Then it goes into examples and solutions, and another example with the solution. 7-8 moments of the area of the moment of the area. L is defined as the second moment of the area, defined as follows: the moment of an area is equal to the derivative of y squared times the distance times the area. Moment of an area y is equal to the derivative of x2 squared over the distance times the area. Area of the moment of the area, branch of the resistance bending of the need to calculate stress due to the bending of the refer to table 72 equation moments for the area with the common shapes. Polar momentum of an area, second moment of the area with respect to the xz axis of the representative of the resistance of the twisting knee with the calculate shear with the truss due with the twisting. J is equal to moment in an area equal to the derivative of the radius times the distance area with the derivative equal to the derivative of the x2 dA plus derivative y2 dA equals the derivative of x plus derivative y. Mass moment in an area is similar with the area moment of an area except the area is replaced with the equation 724 mass. And moment in an area is equal to the derivative of radius times the distance times the mass. Mass moment in an area, measure of the resistance of the body, rotational acceleration, need with the dynamic problem with calculate force moments, acting rigid body in rotation referred to 7-3 with the moments of an area in area common shapes. 7-2, 7-3. Alright, partial axis equation. Calculate the moment in an area with respect to the axis of the parallel centroidal axis. Following the equations can be defined. And moment in an area is equal to moment in an area times area distance squared. And moment in an area, repeating continuous moment in an area times mass times distance when repeating moment in the area, either centroid mass or the area moment in area. Parallel axis equation, moment in the area is centroid mass area of the moment of an area. Alright, radius gyration. Radius gyration K represents the distance of the axis of the area, the mass of the concentrated with the amount with the area to remain the same. Following equations, you then calculate the radius of the gradient. Radius of the gradient gyration is equal to the square root of an area over area, and x equals radius of the gyrant equals over the square root of an area over mass. Alright, 7-7, the summary in this chapter, the shape of the body for the rest of the presented with the important points to discuss in chapter as follows. 1. Particle equilibrium result with a force acting particle must equal 0 with a two-dimensional probability condition result with the two equations which are logarithm fx and f of y. 3-dimensional problem with the coordinate with the result 3 actions x, y, z logarithms equal to 0. Rigid body with the equilibrium result and force moment with the equal to 0. The two-dimensional problem with the coordinates result 3 equations which are logarithm x equal to 0, logarithm y, force y equal to 0, with the momentum equal to 0, with the three-dimensional problem with the coordinate result of the equation which are logarithm x and y equal to 0, the logarithm and force z equal to 0, logarithm mx, my, and mz equal to 0. When drawing a free body diagram and a rigid body, remember to show all the external reactions with the develop the result of the connections support with the type of the number of the reaction with determined as follows. If the point of rigidity cannot translate with a force reaction along the line of translated to x, y, or z, but is required with the point connection can rotate moment of reaction about the axis is required to determine if the member of the two-force member is under the action of the only two force acting on the different points of the member. When analyzing a truss structure, the following important points shall be considered if using the method of the joints. Remember that you can have more than two unknown forces per joint, and using logarithm at force x with 0 and force y 0. If using the method section, remember not to cover the three members at the time, using logarithm at x and y force equal to 0 and the logarithm of momentum equal to 0. The friction members will remember the following points. If an impending motion is not specified, assume the system is equilibrium, then the solve of the friction normal force. Force is equal to static friction with a nominal less than nominal stiction, normal force system equilibrium frictions or forces are calculated correct. If the force is greater than the static and the normal force of the system and the motion and the particle problems will only correct the value of the friction force. Force is V with the kinetic energy times normal force. If the pending motion is specified with the friction force rate, maximum value of force is equal to force max time the static friction normal. Maybe you have the appropriate equilibrium equation solve the unknowns. When you have the parallel axis, the area of the area is equal to the area of the distance, or area equal to the repeated area of the mass distance. Remember that an area is the centroid area of the mass moment of an area. Practical problems, engineering. Alright, we're moving on to Chapter 8, Engineering Mechanic Dynamics.